to both start and finish this topic today, which means that I'll have cleared both Homework 5 and Exam 1 material at the end of today's lecture. So what I will do, when the time comes, I'll say draw a big line in your notes. Everything from this line and above is Exam 1 material. Now the force of friction, there's a reason why I'm introducing it last out of all of these, because it is by far the most complicated. If we didn't live in a world that was basically, friction was so ubiquitous, we probably wouldn't even try to tackle this kind of force. It's a very complicated force. But because it's so prevalent in the world we live in, we need some way of modeling how to include friction in a problem. And what we actually do is we employ a formula that is empirical. So what that means is this is just a kind of patched together thing that sort of works most of the time for most situations, and it's derived from experiment. So it's not worked up from fundamental principles or anything, it's just a kind of rule of thumb. So let me give you an example. So we have some kind of block, and it's on some kind of horizontal surface, and I'm trying to draw it on a kind of a 3D view. Now, if you were to go ahead and zoom in on what exactly happens microscopically that's responsible for friction, it's because the surfaces are not smooth. They kind of look like this. So this might be the bottom of the object. This might be the surface it's on. On a microscopic level, they're not really flat. So there are going to be places where these surfaces interact. Not everywhere, but in many places, there will be sites of interaction. I might represent that over here. I guess I can go over here, try to draw a little 3D view. I might represent these by little dots. So these represent the kind of microscopic interaction sites that you will have. It's certainly not the entire bottom of the object, but it is many places where they will interact. Now it turns out that if I were to increase the contact force, so let me redraw the picture. If I were to somehow push the object harder into contact with the surface, then I'll create more of these. So if I push down like this, then I will get more of these. Something like that. This is, by the way, especially true if one or both of the materials, the bottom of the object and or the surface it's on, tend to be very bendy atomically so that the nooks and crannies can all kind of get more comfortable with each other. And what it's found is empirically, that means by experiment, to a very high degree of experimental certainty, the force of friction is proportional directly to the contact force between the object and the surface. So that's just an experimental fact that you'll have to believe me. And so what it means is that if you push the object and the surface together twice as hard, then the force of friction will be twice as much as well. Now, hopefully that does not come as a huge surprise, right? If you talk about how much friction you experience like this versus if you push your hands together harder, right, and increase the contact force that you have between them, it also increases the friction of the two sliding against each other. The only part you really have to believe me is that they are directly proportional. Okay? That's, if you measure it very carefully, you'll find that if you push your hands together twice as hard, then the frictional force is also twice as hard. Okay? So, with that in mind, we just have to figure out what is the proportionality constant. The proportionality constant is called the coefficient of friction. Actually, I'm jumping the gun here. I forgot one thing. The first thing is how can we quantify the contact force? How hard are the two objects pushed together? Common misconception is that it's equal to the weight. Now, you would not be wrong here, because the force of gravity, of course, is the thing that might pull an object down and make it push into the surface. But over here, of course, it's not that this object has any more force of gravity. You're just adding an additional pushing force that is creating more contact. And of course, we shouldn't quantify it as gravity if we're doing it sideways, right? So the contact force can be also non-gravitational in nature. Now, the one way that we can kind of figure out how to quantify it, of course, the normal force needs to kill any and all forces that act into the surface. It's the normal force's very job to take all the forces that are creating that contact and make sure that they don't actually cause motion. So in this case, the normal force needs to cancel off the force of gravity. In this case, the normal force is even larger because it needs to cancel off both of these. So the fact that the normal force needs to cancel off any and all contact force makes it a perfect aggregator for how much contact force there is. So the normal force measures the amount of contact force. The amount of normal force is a perfect measurement of how hard the object and surface are being pushed together, because it's the very force that needs to make sure that those forces don't actually cause motion into the surface. Is there a question? No? Okay, so what we have is the force of friction is proportional to normal force. Now, this is actually a strange statement because it's actually coupling two forces that are acting normally on different axes. So we're taking, let's say the x and y axes look like this. We are saying that a force that acts in the y direction has bearing on a force which will be in the x direction. So there will be some relationship between what happens perpendicular to the surface, contact force, and what happens parallel to it, frictional force. So this often couples the x and y directions. We're saying that something that happens in one axis can affect something that happens on a mutually perpendicular axis. Now again, that shouldn't be a surprise, okay? Vertical forces affect horizontal forces, right? And then, now that I've mentioned how we're going to quantify contact force, the proportionality constant is this thing called mu. Now, mu is unitless. So we mentioned that everything in this class had to have units, with exceptions where it's ratios of like quantities, and this is such a thing, right? Mu is the ratio of how much frictional force you get over how much contact force you have. Now this is empirically or experimentally measured, and how much frictional force you get for a given amount of contact force is not the same for every single surface. This, you think of it as kind of like a multiplier. It's like a power multiplier. If this mu is 2, that would indicate the frictional force is 2 times the normal force. If this was only 1/4, this would mean that the frictional force is much weaker. It's only 1/4 of the amount of contact force. Now this parameter basically is our way of quantifying how rough the surface is. Okay? So different surface combinations. Have different mu's. It's effectively a way of quantifying the roughness. The larger the mu, the rougher it is. So someone goes to the trouble of getting in a lab and sliding concrete across concrete. And they get a sense of just how much frictional force do they get per normal force. Now, again, if you increase the contact force, friction force always increases. But for a given amount of normal force, how much do you get? So let's say you go in a lab and you measure that for a given amount of normal force, contact force, you get half of that frictional force. Then for that surface combo, mu would be 0.5. So you go and you measure concrete against concrete, concrete against wood, ice against ice, ice against Teflon, right? And you can get a number that describes how rough or smooth a surface is. Okay? As far as limits on this value, well, mu of 0 indicates perfectly frictionless. There is no such value, of course. There is no such surface where no matter how much contact force you put, there's no friction force of any kind. A common misconception is that this has to cap out at 1. That is not true. It's just whatever you find empirically. This can easily be above 1. I've seen values that are higher than 2. Now, is there something where mu is 1,000? Well, no one's found anything like that. But there's no inherent limits to this. It's just what you go and you find in a lab. Okay? Now, don't get me wrong. Values between 0 and 1 are typical, but it definitely goes above 1 as well. So don't think that 1 is somehow some kind of limit. That's just what you end up finding when you go and you test a bunch of materials, sliding them against each other. Sometimes I will be a little bit lazy and I will say the roughness of the surface. That's being lazy because it also matters what's the bottom of your object made out of. So it's technically takes 2 surfaces to make a mu. But that's annoying to say. So sometimes I'll say the roughness of the surface is mu whatever. Okay? So that's basically our empirical friction law. The amount of friction, it depends on the contact force, and it depends on the roughness. Now here's another issue that we have to contend with, is that the roughness is actually rated twice. There's 2 different ways to rate the roughness. Okay? And I'll explain why that is in just a moment. But we actually have to take the force of friction and we have to split it off into 2 prongs. We have to split it off into the force of static friction and we need to discuss its size and direction and the force of kinetic friction. And we have to describe what are the rules for that. So let me give you examples of what these 2 types of friction are. I'll get my object here. So what you can see is that this object, it is currently at rest along the surface. Now let's say I tried to exert an amount of force to get it moving. I'm pushing on it right now. I'm exerting a horizontal force, and yet it doesn't move at all. So what's the net force? 0. So why isn't it moving if I'm pushing it forward? Friction is holding it back. So static friction is the type of friction that keeps you from sliding an object on a surface. Hence the word static. So this is when an object is at rest with respect to the surface it's on. If you don't know that abbreviation, WRT, with respect to. So when the object and surface are not sliding across each other. Now, that means either they're both at rest or they're both moving. For instance, if you've ever left a coffee cup on top of your car and driven across the parking lot before you remembered it was there, and then you go and you notice it's still there when you stop to get it, you have static friction to thank for that, right? Because they were not, while both the coffee cup and the surface were moving, they were not sliding across each other, okay? Now, kinetic friction is the kind of friction that you might be more accustomed to thinking about when the object is sliding across a surface. So there's relative motion. So this is when an object is sliding with respect to the surface it's on. Hence the term kinetic, right? Kinetic or moving. Although it's relative motion that's important. Relative motion of the object and surface. So, let me put this down here for a moment. It's going to turn out that there's enough difference in how friction behaves that we're going to have to pick which one we're going to use in any given circumstance. Now, it's fairly easy because they're mutually exclusive. All you have to do is the object at rest with respect to the surface, or is it sliding? It can't be both. So you just figure out which one would be appropriate, and then use whichever prong of the force of friction would make the most sense. A word on notation. For the force of static friction, I'll generally write it like this. Force of friction, comma, static. For kinetic friction, force of friction, comma, kinetic. If I want to refer to the sizes, of course, I just drop the vector hat. Now, this is my own idiosyncratic notation. I used it, I don't know where I got it, but it's lost to the sand of time. When you see these normally, it's a lot of writing, so there's a special script F, and the script F is meant to stand for friction. So then you only have one subscript to add, whether it's static or kinetic. So be aware, you'll see that probably more often. So let's talk about what makes them so different. Why is it that we have to have two different approaches for friction? Well, it's not really in the direction. The direction, friction always just tries to oppose what you're doing. So in static friction, it opposes the potential motion So you're not sliding, but you're trying to get it sliding. Friction is actually stopping you from doing that. And over here, for kinetic, it opposes the actual motion. The actual slide that you do have across the surface. What makes them tricky is the sizes. Now, I mentioned already that mu, the roughness, gets rated twice. So that's one thing that's different. And the second thing is that the static friction is a variable force. So it varies. It has a range. And the maximum amount that it can give you is provided by that formula we mentioned. So the roughness times the contact force. The kinetic friction force is comparably easy. It is a constant. So if you know the roughness, mu, and you know the contact force, N, then you know how much force that is. So what I want to do is I want to give you examples of both kinds. And let me start with kinetic friction because it's by far the easier one. There's a subtlety involved in the static friction that I want to get to a little bit later. Are there any questions before I do that? Okay, so the one thing I do want to mention before I jump straight into an example is that there's a common misconception that if you, for instance, want to change the amount of friction, you can change the surface area of the object. Now, you notice that that's nowhere in here, right? There's no term for A, meaning the bottom surface of the object, right? Bottom surface area. So, where is surface area? Now, it's in there. It's just that macroscopic surface area doesn't matter. So we don't need an A term. But microscopic surface area is in there. So how much do they actually talk to each other? So there, take a look. Over here, we had less actual locations where they're in contact. Here we had more. So if we totaled up all of the red dots surface area, we'd get a larger one than over here. Why do we have more here? It's because, of course, the contact force was more. So surface area is in there. It's in the contact force. Okay? So the contact force makes it so that you have more microscopic or less microscopic discussion. Okay? So to give you an analogy, okay, let's say you're hiking in the woods and you're trying to wade across a stream, right? You don't want to get washed away, carried and drowned, whatever. So you want to keep a nice firm foothold on the bottom of the stream. So strategies you could take. Okay? Well, don't walk on the slimy rocks, right? Try to walk on the roughest part you can, right? So, maximum roughness. Wear your backpack. That will increase your contact force with the surface, right? Instead of talking only in a few places, you will increase the amount of microscopic talking you're experiencing with your shoes are experiencing with the riverbed. Wearing a big pair of floppy clown shoes is not going to help you, okay? That will increase the macroscopic surface area, but that doesn't really matter. What matters is how much talking is actually happening. Now you might ask, well, if you really push very, very hard on this, aren't you basically limited in how many conversations you can have to the actual area? Well, sure. But saturating the amount of conversation you can have microscopically is incredibly difficult. The amount of contact force you need before you are actually limited by the length and width of the bottom of the object is a lot of contact force, far beyond what you see in everyday situations. So it doesn't really ultimately matter. You could have an object that has a tremendously large surface area, but if there's very little contact force, you're not actually talking in that many places. So the more important thing for asking how much friction you get is contact force. How hard is the object and surface pushed together? And by the way, you will find that things which are much more malleable on the microscopic scale, like say rubber can bend into those nooks and crevices. So rubber tends to be very sticky, right? Things that are very hard tend to be very slippery, right? Because they can't bend and have all those microscopic conversations. Okay, so let's go ahead and do a kinetic friction example. How might we employ this in a problem? Let's do an example. So I'm going to have a perfectly smooth surface that abruptly turns into a friction patch. And I will have that the givens are that you have a mass m that's given initial speed v initial at some point in the past. And I'm going to also give you the coefficient of kinetic friction. That is a rating of the roughness of the object and surface, the bottom of the object and the flat surface, how rough is their interaction. And I'm going to ask, for instance, what's the time, the stopping time? All right? So let's do it. First, I want to identify the forces that act on this object while it's on the smooth part. Force of gravity, normal force. There's two. Any others? Nope. The pushing force is gone. It was set in motion sometime in the past. There's no longer anything propelling it. Remember, velocity is not a force, right? Velocity is a description of the motion. Force is an outside push or pull from the environment. So how is it that then it keeps on going? What keeps it in motion? Inertia. Exactly. The idea that if you leave it alone, it'll just keep doing what it's already doing. There is no backward force against it yet. It's not yet in the friction patch. So to the extent we can neglect air resistance, there's nothing trying to stop it, so there's nothing that needs to let it keep going. It just has its own inertia. So what's going to happen? These two forces cancel. F net is 0. And it will have constant velocity according to Newton's third law, first law, until it hits the friction patch. So let's draw it again. It's going to have the same exact velocity until it first hits the friction patch. Still has the force of gravity, still has normal force, and now it has one more force, which is what? Friction. And it's going to be kinetic friction. So what do we ask for? We're asked for the stopping time. Now that's one of the kinematics variables. But in order to figure out something about the time, we need to link the forces that act on it to the acceleration that they cause, and acceleration can, of course, be tied to any of the other kinematics things. So let's do it. Well, I'm going to go ahead and pick plus x to be forward, plus y to be like this. I'm going to go ahead and set up the y and x variables. By the way, the reason why I picked these axes is not because that's what you always pick. It's because I know the acceleration is going to be horizontal. So then it'll be all x, right? The y acceleration is nothing. And yada, yada, yada. What we're going to get from the y direction is that these two forces still cancel. In the x direction, I have one force and one force only. I have a completely uncontested kinetic frictional force. So there will be, for sure, an acceleration. In fact, it will be an acceleration against the motion, which means that what happens? We slow down. So we're going to have a velocity that's forward, a net force and acceleration against it. Remember, the net force and acceleration are always the same direction. So if there's a net force against the motion, there'll be an acceleration against the motion, you'll slow down. So let's figure out how much it is. We have our rule of thumb for how much the frictional force always is. The kinetic frictional force will be determined solely by the roughness of the surface interaction and the amount of contact force they have between each other. And luckily enough, if we assume that both of those are the same, so the surface doesn't change in roughness, and of course the normal force doesn't change either, then luckily we do have a constant force, right? So we have a constant force, which is going to lead to a constant acceleration, which luckily we can tie into the constant acceleration equations. So we have a whole prepped kinematics scheme for that. Now notice that we do have to borrow. This is the coupling of the two to each other. Oftentimes, the x and y share something. They share how much the contact force is. Because the contact force we find from the perpendicular to the surface, but it also informs how strong one of the forces is parallel to the surface. So we put in here mg. And we solve here, and we find the acceleration is equal to this. It's in the negative direction. And of course, we can't stop there. This is just our avenue into the kinematics equations. So now we set up our variables in no particular order. We know the initial speed is v initial, and I'm going to put in a plus because that's in the plus x direction as I chose it. What's the final velocity? 0. 0. And the acceleration is minus. Remember, when you're working with these equations, signs are important. So make sure that these are opposite. You're never going to slow down if you don't set the velocity and acceleration with opposite signs. I'm asked for the stopping time. Don't care about delta x, although it would be an excellent question. How far do you slide before you stop? And that lets me choose equation number 1. All right. So if you solve equation number 1, you will get this for the stopping time. It's reassuring that it's not negative. We expect this block will travel into the future time, not the past. Remember that g itself is not negative. V initial is the speed, and the roughness coefficient is also always positive. Let's check out a couple proportionalities. Okay? Doing these problems symbolically gives us access to a whole new window of insight that you don't necessarily have if you're just plugging in the numbers. According to this equation, if we slide the block onto the surface faster, what should that do to the stopping time? Increases. Makes sense. If you arrive at that friction patch going way, way, way faster, it should take way, way, way longer before you finally stop. In fact, this equation tells us that they are directly proportional. T is proportional to V initial, which means that if you double the initial speed, what's going to happen to the stopping time? Also double, right? They are directly proportional. So proportionality's a skill that is really useful. According to this equation, if you increase mu k, what should that do to the stopping time? Decrease it. In fact, T is proportional to 1 over mu k. Does it make sense? Just head check that if the surface is rougher, it'll stop more quickly? Yes, it does. And in fact, the proportionality tells us that if it's twice as rough, it'll stop in half the time. If it's 4 times as rough, it'll stop in a quarter of the time. So, useful insight when you solve a problem like this. You can even do it with G if you want. What if we were somewhere where G was stronger? What would happen to the stopping time? It would decrease. T is proportional to 1 over G as well. So we were somewhere where the pull of gravity was even stronger. Now, the surface isn't rougher, but why would the pull of gravity being stronger cause the stopping time to be less?
Increase the contact.
Increase the contact, right? If gravity is stronger, it pulls the object harder into contact with the surface. So that's why the friction increases, not because the roughness increased. Okay? So if you take this table anywhere in the universe, it's equally rough. But gravity might pull something harder into the surface somewhere else. Okay? So that's kind of an example. And I know this is all symbolic, but this is kind of what we're moving towards. And also gives you a sense of how you can tie in all the Newton's law stuff into the old kinematic stuff. It happened to work here, of course, because the acceleration is constant. But that's what we generally expect. If the roughness of the surface doesn't change and the contact force doesn't change, this will be a nice, tidy number, which you can count on as being true for the entirety of the slide. Are there any questions on that example before I move on to static friction? Yeah?
So, in this example, though, the roughness of the surface was changing kind of halfway through.
Well, it changed from 0 to non-zero.
Okay, so it's
But what I'm saying is, like, you don't have like a slightly smoother part here and then a much rougher part here, because then the coefficient of friction would be some kind of function of time, and we don't deal with stuff like that.
Okay, and then our acceleration wouldn't be constant.
Right, it would change if you slid on the different parts. N would be the same, but the coefficient would be different, and that would be a hard thing to do.
Well, you would have to like make equations for each.
Right, yeah, I mean, you could, if I wanted to, I could tell you it's this roughness for this distance and then this roughness for this distance. I guess what I'm really talking about that you need calculus for is that the roughness changed continuously as a function of position. That's the kind of thing you need calculus for. If I gave you a bunch of different sections, mu k is this, and it gets smaller, then it gets bigger, that'd just be a pain, right? You just have to chase it through each section. It wouldn't be impossible, it would just be repetitive, right? Are there any other questions? Okay, so this force is pretty easy because once you know what it is, you can count on it to be that throughout the slide. This being a variable force is what really makes it a pain. So let's talk about static friction. Now, just to make our discussion a little bit more tangible, let me suppose, just for example, that I calculated mu sub s times n to be 5 newtons. Okay? So I figured out the roughness, figured out the contact force, and it just came out to be 5 newtons. Okay? So then I can refer to 5 newtons instead of saying mu sub s times n, which is kind of a mouthful. Okay? First of all, when you see statements like this, be careful. Okay, this is not mu sub s newtons, right? It's mu sub s times the normal force. So this is not the same n as this n. Okay? So for static friction, that means that the frictional force could be anywhere from 0 up to 5 newtons. Okay? So then the question is it 0? Is it 5? Is it something between? Well, in order to figure out how much it is, you have to look to the context. You have no way of knowing if it's 0 or 5 or somewhere between until you look at what else is happening. Let's give an example. So I have an object here on the surface. It's at rest. I'm going to put pushing forces over here, and I'm going to put static frictional forces over here. So here's going to be my object. Okay, first things first. I am not pushing on it at all. How much does static friction have to exert to stop me from pushing it? Nothing. So this is 0. So this doesn't have to do anything. If static friction is the kind of force that keeps you from moving something, you're not trying to move it, it has nothing to do. A common mistake is to want to always say it's 5 newtons. It's not always 5 newtons. If I wasn't pushing on that thing and there was 5 newtons this way, what would it do? Just spontaneously come towards me? No, it doesn't do that. So it's not always 5 newtons. Let's try another one. I'm going to push on it a little bit. Let me push on it with a force of magnitude 1 newton. Is it going to move? No, 1 newton's not enough. How much does static friction have to hold back? Is it 5 newtons? No, it doesn't have to do that much. It only has to exert back, how much? 1 newton. So notice what I'm doing is, I am not being overly obsessed with this mu sub s times n business and wanting to throw that in there. What I'm doing is simply asking, there's forces trying to move it. It's not moving, therefore, friction must have killed them. Okay? So this is oftentimes how you get the static frictional force. What you do is you say, you take a look at an object. The object is able to stay at rest. And what you reason is that it's able to stay at rest because the sum of all the forces that are parallel to the surface that are trying to move it are being canceled off by the static frictional force. That is a great way of finding how much friction acts in a given situation. Is to say, looks like there are forces trying to get it going. Why isn't it going anywhere? Well, friction has to hold it back. Okay? So let's try it some more. Okay? What if I try to push a little harder? Now, let's say I push with 2 newtons. Is it going to move? No, it's not. Maybe that 2 newtons isn't just a single force. Maybe that 2 newtons is due to 17 different forces acting either totally or partially parallel to the surface. And all of those added together is 2 newtons. It's not going to budge because static friction is able to hold that back. This is going to work all the way up until 5 newtons. I can push 5 newtons and this can keep up. So, all of these cases, the net force is 0. And the object can stay at rest. However, at the bottom picture there, it's holding on for dear life. We have said 5 newtons is the most it can do, and now it's doing that very thing, right? So if we pushed even slightly harder, what would happen? It would have to move. The static friction can't keep up, will flow anymore, okay? So what we have is, if you were to push with ever so slightly more than that, so how much is that? 5.0001 Newton, okay? Ever so slightly more, then static friction cannot cancel that, and it will move. So it will accelerate, and it will start moving immediately from rest. So that right there is the essence of why static friction is a variable force. It varies as needed to keep the object at rest. So it varies as needed. And I emphasize as needed to keep the object from rest, or keep the object at rest. It's not our first variable force, by the way. Normal force itself was variable, right? If I push into the surface at 2 newtons, it pushes 2 newtons back. If I push in harder, 5 newtons, it pushes 5 newtons back. The only difference is that we didn't set any kind of upper limit to it, right? I push with 1,000 newtons. If the surface doesn't break, it pushes 1,000 newtons back. This is also variable, but it has a very clear breaking point. And you can calculate that breaking point using this formula. This determines how much can friction hold back before you break its ability to do so. And obviously this limit is going to have to be set differently based on the scenario. The limit is higher if there's more contact force between the object and surface. The limit is also higher if the surface is rougher. But what we calculate when you calculate mu sub s times n, that is the most that friction can handle, static friction can handle in a particular circumstance. Okay? When I give exams, one of the things I can always trick some students on is to get them to just plug and chug and basically calculate the equivalent of 5 newtons or something, and then only exert 2 newtons of force, and they want to say it's still 5. If you only have 2 newtons trying to move it, it's only 2 newtons that it needs to resist. So what you look, oftentimes, you look at the forces trying to move the object parallel to the surface, the frictional force will cancel just those, no more. Okay? Question?
Does that mean that the max amount of static friction you have is equal to kinetic friction?
Well, the coefficients are different, and I'll talk about that. So mu sub s is different than mu sub k. The values are different.
So when it starts moving, it doesn't just become kinetic friction?
It does, but you have to use a different coefficient. So I'll compare the two to each other in just a moment. Okay, so that's the important takeaway from static friction. Now you might wonder, what do you use here? Well, if it moves, you have to use kinetic friction. So it's one or the other. You should never use both. So another way to think of it is static friction is the force you use when the object stays at rest. And kinetic friction is the frictional force that you use when you're moving, even if you move from rest. Now, if that seems like a contradiction, I'll explain a little bit more about that in a little bit when I compare the two frictions against each other. But the point I'm trying to make here is that your friction is complicated enough that we need a separate attack for kinetic and for static. We need to pick which line of attack we use. You can't use them both because you're double counting a single phenomenon. Okay. Are there any questions before I do an example? Yeah.
Make it really quick. When you're saying like on an exam when students the plug and chug thing, you put like 0 to 5 and they would just assume that it was 5.
Always 5, yeah.
Okay. How is it that it wouldn't be, like how would they end up if they had done it the correct way to get like 2, for example?
They would calculate how many forces act parallel to the surface, and they figure out it totals out to only 2. And then you realize, well, static friction could exert up to 5 if you need it. It only needs to exert 2 newtons because there's only 2 newtons trying to get it moving.
So that, so 2 would be the answer.
Right.
not 5.
Exactly. You would have some way of figuring that out. You could tally up that you have so and such a force trying to move it, and then you say, hey, but it's not moving, so I guess that amount of force is provided by friction the other way. It will not exert its maximum for you just because you feel like it. It'll exert its maximum when it's needed. Right? Question?
So you would need to know its maximum in order to calculate if the new sub K comes into play at all, right?
Right, so the way that this comes in handy is that this gives you the threshold above which you have to push to get something moving, right? So it tells you how much it could resist to up at the most. Yeah?
Well, when you're talking about like static friction on like an incline.
That was a very example I was going to do next. Any other questions before I do that? Okay, so let's do that. So let's do kinetic friction on an incline, or static friction on an inclined plane. Here, I'll draw a little rough surface to indicate it's not frictionless. Although in practice, a safe assumption from here on out is that unless friction is explicitly discarded, you should probably be willing to consider the fact that there is friction. I had a fully numerical question, which I don't seem to have here. Okay. Yeah, let's do it numerically. If you guys wouldn't mind helping me out with the calculator, I'm just going to make some stuff up. Okay. So let's have a mass of 1 kilogram. It's going to have an incline of, I don't know, 20 degrees. Let's say the coefficient of static friction is 1.2. And here is going to be my question. So part A, how much static frictional force is needed? What is the static frictional force acting in this situation? And B, what is the maximum angle at which I can tilt this and have it still stay in place? Or I guess I should say that this is initially placed at rest. So the mass is initially at rest. All right. So let's try it. I'm going to go through steps 1 through 6 like a recipe. Problem-solving strategy with forces, it works. Okay, it should work for every problem on homeworks 4 and 5. So first things first, object of interest, obviously this mass. Step 2, identify forces on it. So what's the force? Gravity, that's one, straight down. And what was the other one? Normal force. Perpendicular to the surface, holds the object away. That was the inclined plane without friction, right? Now we know that if it was just those two forces, it would accelerate downhill. But remember that friction acts against what you're trying to do here. So which way does the static frictional force act? Against that. So uphill. And that's it. Those are my three forces. All right. So now, once I've identified the forces, I pick a x and y axes. If there is an acceleration, I try to pick one of my axes along that. Here, I specifically want it to stay at rest. And I'm going to show you that it does stay at rest. So that's not a consideration. So instead, if the acceleration is 0, what do I want to do instead? What's that? Minimize the components. How might I do that?
The axis along the incline.
Yep. So same as before. Same as I did on the incline previously. That means that 2 out of the 3 forces don't need any kind of SOHCAHTOA treatment. They're already along my coordinate axes. And the one I do need to break up, I've already done it. Because it's the same thing as I did on the frictionless inclined plane. So I break up the force of gravity into 2 components, one that's directly into the surface and one that is parallel to it. Let me remind you of what we did. We discovered that this angle is the same as the angle of the incline. And then we do the SOHCAHTOA. Let me just put it in the free body diagram. Here's what we have. So there's our free body diagram. So we can look at the pushes and pulls along the coordinate axes, independent x and y pulls. So let's take a look. A good free body diagram pretty much tells you what's going to come out of the equations. Question?
Sorry, just real quick, how do you know to use sine and cosine for?
Same as the frictionless incline plane, so it's in your notes from last time. Just don't want to have to repeat it. Yeah.
The initially at rest given qualification, I would think that to me almost implies that it's economic as opposed to just being like stays at rest.
Well, you're right. I should have phrased the question better. I should have said it's initially at rest, it stays at rest. I'll show you, I'll prove to you that it does stay at rest.
Okay.
Are there any other questions? Okay, so there's still this offending component of gravity that's trying to move the object into the surface. Normal force still says, excuse me, solid surface here, let's cancel. The y direction is exactly the same as on a frictionless inclined plane. Whether or not you're sliding parallel to the surface or not, the surface still does not like you going into it. So, at the end of the day, what you have from the y direction, F net y equals MAY. This is going to just give you the same thing as before. So that's true regardless. It's the x direction, of course, that's different. Before, mg sine theta was the only uncontested thing parallel to the surface. Now, static friction says, where do you think you're going? Okay? So let's put the x direction down. Now we have no x acceleration either. So what do we have? We have that, sure, mg sine theta is trying to get it to slide, but now it has competition. And we go ahead and we solve for how much it has to be. So right there, we have by inference found how much static friction has to be. It's this statement right here. We look at the forces that try to move it, and we infer that it must kill them. What's trying to move it? mg sine theta. So what is this number? 1 times 9.8 times sine of 20. Someone tell me what 9.8 times sine of 20 degrees is. 3.35 newtons. Okay, that is how big static friction is in this particular case. Now, let's take a look at common mistakes, right? Students want to say the static friction can be anywhere from 0 up to mu sub s times n, and they want to say it's always equal to that. Let's find out how big that is. Mu sub s times mg cos theta. That's the contact force when you're on a surface. So can anyone tell me what 1.2 times 1 times 9.8 times cosine of 20 is? What is it? 11.05. So that tells you that in this circumstance, the force of static friction can be anywhere from 0 up to 11.05 newtons. Should that be necessary? Is that necessary? No. You only need 3.35 newtons because that's the only amount of force that's trying to actually get it going, right? Just like over here. It doesn't need to be 5 if you only need 2. That's what we found over here. Realize that when you're calculating mu sub s times n, you're calculating the maximum amount that friction could be, but that doesn't mean it always is. So here, we found you're actually somewhere pretty low in this range, because you just don't need that much. Okay? Are there any questions on part A before I do part B? Okay, so let's do part B. Now, in order to kind of preface part B, let me take a look at what happens when you go from a relatively flat incline to a very steep incline. When you're on a relatively flat incline, the force of gravity, as you probably notice, is almost entirely into the surface with a very, very weak parallel component. So what you have here is you have lots of normal force. Remember, the normal force has to cancel that. And if you have lots of normal force, you will have a very large maximum value to your static friction. So friction could be very large if necessary. However, the force actually trying to get you moving is very, very tiny, which means that friction needs to be relatively tiny, right? So the force trying to move the object, which is mg sine theta, is very small. And what you will find is that the static frictional force is way less than it needs to be to hold such a little tiny force back. That's kind of what we just saw. We saw that in part A, right? You needed 11, you could have held back with friction up to over 11 newtons. And yet you only needed about 3. Now when you start to tilt it, it starts to kind of go in a different way. If you start to have a very steep incline, what happens is now the component into the surface starts to be very small, and the component trying to move it is very big. So now that's kind of 2 hits against friction, right? The contact force is getting smaller. The normal force is getting smaller, so N, and therefore the maximum that static friction can exert, are getting tiny. You have less contact force. And yet, mg sine theta, the force trying to move it, is increasing. So that's a double whammy, right? The force trying to get the object moving is larger, mg sine theta. The contact force, which is what helps the friction force be larger, that's shrinking. And you can see this is going to come to a head at some point. What's going to happen is the definition of theta max is when mg sine theta is so large, it has grown to require the entirety of the force of friction. So it's going to need every last bit of fight for the static friction to hold back mg sine theta. So let's calculate at what point does this come to a head. Well, luckily, since we did this symbolically, we can largely use our work from part A. So this is the kind of language that allows you to realize that it's okay to use or invoke the maximum frictional force. By definition, when theta goes to theta max, you're asked about some extreme case like the maximum tilt. That is what allows you to take your static frictional force and invoke its maximum value. So look for language like that. Look for barely holding on, or just about to slide, or something to that extent, or the maximum angle you can tilt it before it slides. So let's write down our equations. Here were our equations. And let's do it. We're now at the maximum angle, theta max. The definition of theta max is friction force is maxed out. Well, we have an equation now for that. That's mu sub s times n. And hey, here's n over here. So now we can solve for what theta max is. That right there is a statement which basically equates mg sine theta, which is the force trying to move the object, and sets it equal to the maximum frictional force trying to stop it. So we're trying to find out at what angle does mg sine theta actually request every last drop of what the frictional force could offer. Let's solve. The mg's cancel. Solve here. Leave the algebra to you. You'll get it's the inverse tangent of the coefficient. Can anyone tell me what inverse tan of 1.2 is? What is it, 50? So let's call it 50 degrees-ish. It's bigger than 20, right? Have no problem holding that object at rest at 20 degrees, right? In fact, it had room to spare. But if you tilt it up to 50 degrees, then static friction is holding on for dear life. If you tilted it even slightly more than that, it would slide. Because then this force would get even larger and this would get even smaller, right? Because as you tilt it, the force trying to move it grows while the forces trying to hold it in place get weaker, okay? You will can confirm for yourself that the larger value of roughness you plug in, the larger theta max gets. So if you have a rougher surface, you can hold it in place until a higher angle. I also want to point out as a final thing, the mass itself is gone. That's something you may not have noticed if you didn't do it symbolically. One of the ways I can make you do it symbolically is to not give you things I know will cancel eventually. It seems strange that the mass doesn't matter. It's just saying it will stay at rest up to 50 degrees if it was a 1 kilogram or 1,000 kilogram. Anytime you see a variable that's surprisingly not in the answer, go back and see where it canceled and try to reason out what happened. If your mass is larger, yes, your force trying to move it is larger. But guess what? So is the force that's creating contact. So yes, there's more force trying to move it, but there's more force holding it in place. Of course, both those components grow together because they're just components of the force of gravity. One component of the force of gravity tries to start it, the other one helps to hold it in place. And of course, if it's in both places, the mass doesn't really matter. Okay, so that's it for today. I'll compare and contrast